So first, there's FEVU. If you don't know FEVU, FEVU is electric force, electric field, electric potential energy, and they're represented with these letters, and it looks like FEVU, so that's how I help myself remember these ideas. Now, this is hard. Obviously, this test is going to be more conceptual than just cranking out calculations, because it's a 45-minute take-home exam, and you're going to be like probably having to explain things in words more than other years. And there's still going to be calculations, I presume, but there's going to be more conceptual. So it's important to understand the concepts more than just memorizing formulas. So these all get cluttered in people's mind, like the electric force, the electric field, the electric potential energy. People have one folder, mind folder, and they stick all of these in, and when the time comes to grab an electric something, they grab something out randomly. Oh, I didn't even mention electric charge. That's a fifth quantity. So we're going to keep all these in track. The first thing, we'll start with the simplest. The first thing to know is that you have to have electric charge in order to interact with any of this. You won't see any of this FEVU unless you have some electric charge. That's the name. So all these have a name. That's the name. It has a letter. The letter is Q. And it has a unit. The unit of electric charge is coulombs. So you got to keep these in mind. There's a name, letter, typically a formula. There's no formula for electric charge, and a unit. So let's go through and do that for all these. This is F. This is the electric force. How is this different from these other electric quantities? Well, this is a force. That means it has units of newtons, like any force, and like any other force, it's a push or a pull. So this is a push or a pull, just like gravity is a push or a pull, tension is a push or a pull, electric force is a push or a pull. Where might it find a home? It might find a home in Newton's second law if you needed to. Like that could find its way into there because it is a force just like any other force. It's just happened to be the force between electric charges. So what's the formula? So that's the name, electric force, and the unit is newtons, and you might find it here. Other formulas with force, shoot, you might be like, well, isn't work the integral of F dot dr? Yeah, so like anywhere there's a formula with force, you can imagine plugging this in to find some other quantity, because it's an honest-to-God force, just like any other forces. And the formula looks like this. On the formula sheet, they give you 1 over 4 pi epsilon naught. You might be like, what the heck is that? Well, this is just K. So this whole quantity is that electric constant K. That's what this is. Times Q1 times Q2 divided by the distance between the two objects. So I'm going to use a color like this. Divided by distance between them squared. So if you have two charges, they're going to exert an electric force of this many newtons on each other. It could be attractive or repulsive. You should just use this formula to find the magnitude of the force. And then you're going to decide, all right, well, if they're oppositely charged, they attract. And if they're the same charge, they'll repel. Don't rely on the sign of this formula to tell you the direction of the force. Why? Because look, let's say I had a positive charge here and a negative charge here. If I, that's a bad idea. Let me do it this way. Negative charge here, positive there. If I did it the other way, it would, making a mistake would get the right answer. I don't want to promote that. So over here, let's see, which way is the force on this negative? It's to the right. The electric force is to the right. Which way is the force on this positive? To the left. These attract. However, if you plugged in a negative charge here and a positive charge here, you'd get a negative answer for force. You might think, oh, negative charge for force means these both point left. But one point's left, one point's right. The negative you get out of this just means attractive. It doesn't mean left, up, down, or right, or anything like that. So plug in magnitudes of charge, plug in magnitudes of charge, magnitude of R, and that'll give you the magnitude of F. And then it's up to you to decide, all right, this was attractive or repulsive. Figure out which way that force goes. That's force, electric force, that's in newtons. How about electric field? What is this thing? Well, the name is electric field. This is not a push or a pull. This is different. This does not have units of newtons, but the name is electric field. It has units of newtons per coulomb. You can also, I'll leave space. There's an alternate unit you can give this, but newtons per coulomb is sort of the simplest one to think about. What is its formula? Well, I'm not going to give you the formula like this for a minute. I'm going to show you how it's related to F. So all these will have formulas, all these letters, FEVU, and they'll have connections. And the way this one's connected to the other one is that the electric field is defined to be the amount of electric force divided by the charge that was exerted, that force was exerted on. So if you have some charge out here, let's say you go to this charge right there, and you're like, hey, charge, what's up? It's like, hey, not much. I'm just getting this force on me. You're like, hey, can I just ask you how much force was there on you? It's like, yeah, there was this much force. And hey, I'm giving this poll here. Can you tell me how much charge you had? Yeah, I've got this much charge. Thank you very much. If I take the ratio, that tells me what the electric field was at that location right there. And it's the electric field due to other things. You might be like, isn't the electric field infinite because it's right on top of a charge? We're talking about electric field due to the other things around it. So the electric field in that region is defined to be how much force would be on a charge there divided by the amount of charge. That's what we mean by electric field. It's this ratio of force per charge. That's why it has units of newtons per coulomb. And you'd be like, where's this electric field coming from? It's coming from the other charges. So this positive is going to create an electric field everywhere around it. Just out searching, hopeful that it's going to find a charge out here. So over here, the electric field over here interacts with this charge, causes a force on it, and the ratio of force per charge gives you the value of that electric field. So all charges do this. They all create electric fields, regardless of whether there's another charge to see it or not. This is like the lonely Twitter user sends out a tweet. No one hears it. Doesn't matter. They're going to keep sending it. They keep tweeting. No one's listening. Doesn't matter. They keep sending it. The charge is the person. The electric field is the tweet that someone might respond to, someone might not respond to. And then if it does respond over here, you could get a force, right? You get pushback. Someone's like, that's not good. I'm outraged or whatever. And the force is the outrage, the push or pull. All right, so all these charges are emitting electric fields. How would you find it? Let's say you wanted to predict what it is. You don't want to go out and give a poll on ask these charges questions. Let's say you wanted to predict what it was. Well, look, if I take this formula for force and I just divide by a charge, I'll get the same formula, just minus one of these charges. So the formula for electric field is 1 over 4 pi epsilon naught. You lose one of these charges. Which one? It doesn't matter. Just call it Q over R squared. Same deal. Assume this Q is positive. Even if it's a negative one, just plug in the magnitude, and that gives you the magnitude of the electric field. Because look, the electric field points radially out. It could be pointing up. It could be pointing down. It could be pointing right. It could be pointing left, all from the same charge. So what you're finding here is the magnitude of the electric field at some radius r around that charge. So all charges create electric fields. Positive ones create fields pointing out. Negative ones will create fields pointing in. So if you had a negative charge sitting here and you're like, hey, what kind of field are you going to create? This charge is going to create a field that points radially inward. There's one thing that's confusing here. You might be like, wait, nice story. But the electric field over here from this positive points radially out, so it points left. But look at the force on this negative. The force pointed right. How come this negative didn't feel a force in the direction of E? We'll just look at this formula here. This one you can plug in signs. So if I know which way the electric field points, and I know it points left, that's negative, and I multiply by my charge, which is also negative, negative times a negative would give me a positive force. So that's just to say that negative charges feel a force in the opposite direction of the electric field. You can rewrite this formula. It's easier to think about if you're trying to figure out direction of force this way. You could say force equals, I'm going to do Q times E. Q times E. What this means is if your electric field is left, negative, and your charge is negative, negative times negative would give you a positive. The force would point opposite the direction of E. So if your charge has a negative charge, the force on that charge points in the opposite direction of the electric field in that region. You might be like, wait, doesn't this negative create field that goes toward it? Yeah, but it doesn't interact with its own field. We're talking about the electric field created by other charges. So we're talking about the electric field created by this positive. That's the one that this negative is going to notice and respond to. No one reads their own tweets. That's what I'm trying to say. So yes, this negative sends its own tweets out, but no one, I guess people probably do read their own tweets. I don't even know. I don't even use Twitter, but Let's assume people don't read their own tweets. These charges don't read their own tweets. They only read other people's tweets. They get outraged by those. Oh, that's the analogy. People read their own tweets, but they don't get outraged by them. The only way there'd be a force on a charge is by reading someone else's tweet. You get outraged, and then you there's an impact. There's a Newton push or pull. Okay, that's this left-hand side. There's these two formulas for electric force, electric field. Electric field is like the potential for force. You know what I mean? So force is like the outrage. Electric field is like the potential for outrage. You send out the tweet, and someone might get all triggered and angry about it. The force is like, oh, someone did say it. They all are outraged, and so they're angry about it. So electric field is just sending that out there. If there's any charges in the vicinity, they're going to interact. Now, charges are mandatory, required to react to other people's electric fields. So it's almost like Twitter. Everyone is like reacting to everyone's stuff on there. Okay, and this is how they're connected. So if you want to get from force to electric field, crawl down this way. Divide force by Q, that gets you to E. So these are the connector equations right here. This is how force and electric field are connected. These are how you find force and field from just the raw charges and where they're located, but this square is how you connect the two. Okay, that brings us to the right-hand side. What is this? This person over here, this V, this is electric, this is electric potential. That's the name for it, electric potential. And this top one is curiously named electric potential energy. Now this is unfortunate. Like these sound almost identical. This stuff's already easy to mix up in the first place. So this U is electric potential energy. It's an energy. Well, that's easy to deal with then. I know what unit energy has. Energy has units of joules. You know what I mean? I'm going to write it over here. Units of joules. All energy has units of joules. So this is how much electric potential energy there is. You can throw a little E down here if you want to remind yourself, yep, that's an electric potential energy as opposed to like gravitational potential energy. Where would it find a home? Well, conservation of energy. So if you're doing E initial equals E final, you can imagine having kinetic energies in here and maybe electric potential energies. So it would not find its home in Newton's second law, but it could find its home over here. So then what the heck is this electric potential term? We'll talk about that in a second. Let's start with this one here. So if you've got two charges, they exert a push or a pull on each other. That's the force, the electric force. If you have two charges, they will also have potential energy. That is to say, two charges near each other have the potential to increase their kinetic energy. So, right, if I stick a positive next to a negative, I let go, they start flying toward each other. There's kinetic energy now. Where'd it come from? It came from the electric potential energy. So it's going to be Q1, Q2, just like the force over here, divided by, except it's just R. It's not R squared. I'll show you why in a minute. So this is the formula to find the electric potential energy between two charges. And again, you can, plug this in over here. Maybe they start far apart with a big R and no kinetic, and they end with some kinetic and a smaller R. Just plug this in, you get the right answer. Except here you do get to plug in the signs of the charges. So over here it was confusing. These vectors can point up, left, right, down, and whatever. If this is positive or negative, it's just positive or negative. Like, actually plug in the signs in here, and this will work out. You can have negative electric potential energy. That's okay. Just like you can have negative gravitational potential energy. If you're like below the H equals 0 line, you can have negative electric potential energy. Plug in those charges accordingly, and this will come out accordingly, positive or negative. So you really are finding the sign over here. Don't plug in the signs for these vectors. This force was a vector, complicated. This electric field was a vector, complicated. Figure out these on your own based on opposites attract, likes repel, and positives create fields that point radially out, negatives create field that points radially in. But this one, you can plug in the negative sign and everything works out okay. So how do you get this formula? Well, we have a formula for potential energy, and the formula looks like this. It says that the potential energy, I'm running out of space here, I'm going to write it right here. The change in potential energy is always going to equal negative the integral of F dr. So this is a formula on the formula sheet. It's just, this is true for any force. If you want to, well, any force that can have a potential energy associated with it, which we call conservative forces. So if you're a conservative force, you can do this. You can integrate integral F dr, and the negative of that integral gives you the change in potential energy associated with this force. So if this was gravitational force, you'd be finding change in gravitational energy. But here it's electric force, so we're finding change in electrical potential energy. So what if we did this? What if we put this formula right here for force into this integral? Well, you'd have the integral of 1 over r squared. That's the only like variable dependence here. All this stuff is, all these charges are constants. Bring them out front. So what's the integral of 1 over r squared? That would be the integral of r to the negative 2. Well, that would be, you know, r to the negative 2 plus 1 over r to the negative, so it'd be negative r to the negative 1. And what would that do? Well, you'd have r to the negative 1. That's why r squared becomes r in the denominator. So it's now 1 over r. Negative 1 over r. You might be like, well, where did the negative go? It canceled with this negative. This negative is always out front. So when you take this integral, you'd get a negative out front. It would cancel with this one. That's how you just define a potential energy. That's what we get. You might be like, wait, but this is the change in potential energy. And I just wrote potential energy here. Yeah. So what we do is this. We say, okay, look, you have to pick some point where your potential energy is going to be 0. Let's just start from infinity and then come into some point r. You're like, why? Who in their right mind would ever let you start from infinity and come into r? Well, it's a good thing, because if you ever stick infinity down here, you just get 0. So that limit just gives me 0 when I plug in, because 1 over infinity is 0. So if you plug in 1 over, infinity for r, that one gives me 0. What would the r one give me? It would give me this. And so over here you would have u at r minus u at infinity. That's 0, this limit here. And we just define, okay, this is an additional assumption. We're just going to be like, let the electric potential energy be 0 at infinity. Why not? No one's going to go there anyway. Let's call it 0 there. And we call it 0 there because this, this formula is going to have a 0 value there. So if you plug in infinity here, you define potential energy as 0 at infinity, you get a formula for just the potential energy, not just the change in potential energy. Maybe you wanted the change in potential energy between A and B. Great. Plug in A, plug in B. You'd get the value at B minus the value at A. That'd be the change in potential energy. But this is the formula that connects force and potential energy. Sorry, this is getting a little messy. That lets you go from force. If you have force and you want potential energy, take it into here, crank that integral out, you get this one over here. Can you go the other way? Look at, if you had force, you want an electric field, divide by charge. If you have electric field, you want force, multiply by charge. What if you want to work back the other way? Well, it's not too bad. Just, fundamental theorem of calculus here. You could turn this integral into a derivative, and what you get is that the force, the electric force, would just be negative the derivative with respect to r of the potential energy. So I'm out of room, but if you move the negative over, take derivative of both sides, you're just going to get, force. The force is going to be negative the derivative of the potential energy. So this is a way to walk leftward. But again, it's like this test is not all about just memorizing formulas. What does this mean conceptually? Look at what this says. It says the electric force points in the opposite direction of increasing u. So if the slope were positive here, this is the slope of u. So say u was positive. F is going to point opposite that direction. In other words, downhill. So the force on a charge always points toward lower electric potential energy. Like there's a story behind this formula. It says there's a force on every electric charge that points toward lower electric potential energy, and the more you can change your potential energy per space, the bigger that force is going to be. So if I can go from one point to another point very close by and change my potential energy dramatically, I'm going to be really motivated to do it. If I sort of change a little bit motivated. So that's where this derivative comes into play. What does that mean? Okay, so we got this positive and negative over here. If I let go of this negative but hold the positive fixed, so I hold this in place, we know the negative is going to fly to the right. So the negative is going to sort of fly to the right. Actually, we'll do it the other way. Let's say we hold the negative still and we let the positive go. The positive is going to fly to the left. It attracts to this negative charge. So one way to explain it is that opposites attract, sure. Another way to explain it is there was an electric field from this negative pointing inward toward the left, and positives point with their forces toward the same direction as the electric field they're in, leftward. Another way to explain it is, look at this negative charge. It's creating a negative lesser potential energy if this charge comes nearby. Why? Because you'd have a positive and a negative. It'd be negative up top. And R would get smaller. You'd be getting a more and more negative value. So if I have a negative charge and a positive charge interacting, that gives me a negative value up top. What do I do to make this value smaller? I want my R to get smaller, because that would give me a more and more negative term. Like this would go from negative 10 to negative 20 to negative 30. It's decreasing. So that's what this positive wants to do. This positive is like, what should I do today? Look at this formula. It's like, I should decrease my potential energy. How do I do that? I'm going to move leftward, reducing this distance. If I reduce that distance, I'll make this term more and more negative. I'm going to reduce my distance between me and this negative so I can reduce my potential energy. That's what I'm going to do. How do I do it? I feel a force that way. So there's a force compelling me to move in that direction toward lower potential energy. That's what all charges want to do. Even negatives want to move toward lower potential energy. This negative is like, what should I do today? I'm going to move right, because same argument, positive and negative up top. Like you can swap them if you want, positive and negative. Still negative up top. Reduce R in order to make this U smaller. Every charge in the universe is trying to reduce its potential energy, its electric potential energy. So what is this remaining V down here? Why does it sound so similar to electric potential energy? Because just like E, this E is F over Q. This V, the electric potential, is U over Q. So if I take, so I'm going to do the same thing. Watch, I'm going to take U, I'm going to divide by Q. So basically I could be like, all right, look, I'm going to come back and do another poll. Except, you come up and they're like, oh God, it's this guy again. What does he want? I'm like, I'm doing another poll. Can I please ask you charge? Can I ask you positive charge really quick? What's your potential energy, your electric potential energy? And it's like, whatever it is, it's UE. And I'm like, okay, and what is your charge again? He's like, I told you my charge, it's Q. You take your Q. I told you last time when you were interviewing me for the force here. So you take UE, you divide by Q, that ratio, how much joules of potential energy this charge has per charge, is what we define as the electric potential at that point in space. So the electric potential is defined as a value at a point in space. Its units are not newtons per coulomb. So it's not how much force you'd get per charge. It's how much energy you'd get per charge. Again, there's other ways to define this. Sometimes we call this a volt. So this is shorthand. Joule per coulomb, sometimes people call that a volt. But that's just a shorthand. And so this is what you could do. You can come up, interview these charges. Hey, what is it? What do you get from that? Or you're like, man, I don't want to go and bother charges on the street. How could I just figure this out for myself? Well, look, UE is this formula. If I take UE and I divide by Q, guess what? You cancel off one of these charges. Again, just like we did for E, and you're like, oh, that's easy. I get 1 over 4 pi epsilon naught. Cancel off one of those charges, fine. You get Q over R. So that's my formula for V. Again, should I plug in the positive or negative here? Yeah. These can take care of themselves. Plug in that positive or negative and you get a V that's positive or negative. You might be like, okay. Mathematically, I see what you did there. I have no like understanding conceptually of what electric potential means. And that's important because this year, more than ever, the test is going to be more conceptually based than just raw calculation based. So what does this idea of electric potential even mean? We'll look at it. It's how many joules per coulomb a charge would have. So what it means is like, not only is every charge creating an electric field everywhere around it, they're sending out tweets. The electric field were the tweets, sending out tweets that other charges might see. And when other charges see one of those tweets, like the E value is like how much push or pull you'd get per coulomb. So if the electric field had a big value, 1 million, then if a charge interacted with it, you'd multiply that E by the value of the charge. That'd tell you how much push or pull you'd get. Well, the same thing is true for electric potential. There's not just electric field around these charges. So a negative charge doesn't just create an electric field everywhere around it. It also creates an electric potential value everywhere around it. There's a V value mapped out in space everywhere around it. So everywhere around it, it stakes out a V value everywhere around it. Closer to it might be like negative 100. Farther away, maybe like negative 50. Different values at different points in space. Some V value, let's say it's like negative 10. Oh, sure, 110, miswrote. 110 joule per coulomb. What does that mean? Well, it means that if a charge happened to be wandering by, like this does nothing until a charge wanders by. If a 1 coulomb charge happens to wander by, we'll make it a 2 coulomb charge. If a 2 coulomb charge happens to wander by into this region where this negative created a trap, created a negative 110 joule per coulomb, this Q would now have, let's try to see what it would be. It would be Q times V. So you could rearrange this formula. So you could say UE, the amount of potential energy something would have, is going to equal the Q that wanders into some region and multiplied by the V in that region. So this 2 coulomb, minding its own business, is like, oh my God, I found myself in a negative 110 joule per coulomb trap. Who did that? And this negative's like, haha, you activated my voltage trap over here. And you multiply these two. Q is 2 coulombs. V was a negative 110. So the amount of electric potential energy this charge would have would be UE of these. It's really of the 2 charges together. You know, it takes 2 to tango. If this hadn't have laid the trap down, then this couldn't have had the potential energy. So it's kind of potential energy due to both. But the potential energy in this system would be negative 220, simply by multiplying these 2 joules of electrical potential energy. You might be like, negative electric potential energy? How can something have negative electric potential energy? Like, wouldn't these still attract? Like, if I have a positive here and a negative and I let go of them, don't they attract each other? Yes, they do. And you're like, doesn't that create kinetic energy? Yes, it does. How can you create kinetic energy if you started with negative potential energy? You just go more into debt. So these are going to attract. The R is going to get smaller. What happens if the R gets smaller? You get a more negative number. Like, that's a more negative number. You just go more into debt. Like, everyone understands this. If you're in debt, doesn't mean you can't buy stuff. If your budget, if your bank account right now is negative 220, you can still buy stuff, get a credit card. You go more into debt. I'm not saying it's a good idea, but it's possible. Like, these charges can still buy themselves some kinetic energy. It's just this potential energy would go from like negative 220 to negative 320, and that means your kinetic energy would be 100. If it goes from negative 220 to negative 420, then your kinetic energy would be positive 200. So you can still gain kinetic energy if you have negative potential energy. It's just you'll have to become more and more negative potential energy. So charges, in summary, create electric fields around them, sending out tweets, hoping some charge wanders by and sees it. If a charge wanders by and sees it, there's going to be electric force on that charge. Those charges also create electric potential everywhere around them, but it doesn't have a direction. It's just a number with a unit and a like dimension, you know, joule per coulomb. So it's just a number, no arrows. You can't be like, that's the V value. No arrows for V. These are not vectors over here. They're a number. They're a number that tells you how many joules a charge would get if it wandered into that region. So the electric field tells you how many newtons something gets if a charge wanders into a region. It's the amount of like potential force. This is like the amount of potential energy. Maybe that's why they named it so poorly, because potential energy doesn't really flow off the tongue all that well. These are the formulas that connect U and V. Let me draw it better. Those are the ones that connect U and V. So if you know U and you want to get to V, you know, use this top one. And if you know V and want to get to U, use this bottom one here. It's the same formula. That just leaves one gap. Leaves a gap right here. How do we connect E to V? You're like, oh, we'll start with E, go get the F. When you have the F, go to the U, then you come down. Like, that's too long. Is there a way to directly connect these? And there is. Effectively, you can just imagine, look at what we can do here. F divided by Q is E. And U divided by Q is V. So you're like, oh, if you're super clever, you're like, hey, look at this formula up here. What if I just divided both sides by Q? Divide F by Q. I'm going to try to draw it small enough to see it in there. Divide F by Q. Divide U by Q. You're like, hey, you can't sneak that in the derivative. Yes, I can. The Q is a constant. We're going to assume the Q is constant. So you can sneak it in the derivative. Well, what would this formula become? If I divide the left-hand side by Q, I get F over Q, which is E. You're like, okay. So you get E over there equals, and it's a vector, equals negative the derivative of U over Q, because I'm dividing both sides by Q. What's U over Q? U over Q is V. So negative the derivative of V. So if you want to find the electric field, take negative the slope of V. So, you know, this might be represented graphically, beginning again, in words, what this means is that the electric field points toward decreasing V. So if I gave you a map of the V and I was like, okay, here's a map of the V, and right here it was negative 110. You know, that's the V value, joule per coulomb. And out here it was like negative 50. joule per coulomb. And I asked you, in this region here, which way is the electric field point? Electric field points toward lower V. So the electric field is going to be pointing that ways. And that kind of makes sense. Look, it's like toward this negative. I kind of missed a little bit, but it points toward the negative charge is which way the electric field points, toward lower V, just like force points toward lower potential energy. Can you reverse this formula? Yeah, you can. Divide the bottom one by Q. You'd get delta U over Q, which would just be delta V, So you'd have delta V. If I divide U by Q, I get delta V equals negative integral. Again, you can go from infinity to R, or you can go from A to B, whatever you want. We're still going to always define potential at infinity to be 0 unless stated otherwise. What happens if I divide left by Q? I get delta V. What happens if I divide right by Q? I get F over Q. F over Q is just E. Let's get E, dot dr. So these are the formulas that connect the left and the right. Whoops. So this is how you get from electric field to electric potential energy. In other words, if you have the V and you want to get the E, just take a derivative of that V. So, and it works out. Taking a derivative of 1 over R gives me 1 over R squared. So it all works out. If you have E and you want to get delta V or V, if you want V, just make one of these limits infinity and you get a 0 over there. Then you take an integral of E with the negative and that gives you delta V. And delta V is given a special name. So none of these get a special name except for delta V. Delta V is special. Delta V is called the voltage. Some people even call V the voltage. I don't like that. That feels sloppy to me, but delta V technically is a voltage, and so it has units of volts. Last thing here with this FEVU, one little space here. What's another way to write electric field? Well, look, it's derivative of V with respect to R. That's V over space. The units of this would be volts per meter. So this would have volts on the numerator because the unit of V is volts, if you want to write it like that, divided by meters. So an alternate way to write the unit of electric field is volts per meter. Some people like that unit, so don't freak out if you see electric field represented as volts per meter. Okay, really quick summary. Force is a push or a pull between two charges. It's a vector, has a direction, but don't plug in these negative signs. Figure that out for yourself. Opposites attract, likes repel. Electric field is a potential force. It's an electric field a charge creates around it, hoping there's another charge that wanders in the region. If there's a charge that does wander in the region, you can find how much force would be on it by multiplying that charge that wandered in there, multiplying by the magnitude of that electric force. And you can include the sign here as well, and you would tell you which way the force would go. Negative charges feel a force opposite the E, because it would bring its own negative. Positive charges feel a force in the same direction of E. And the formula for E looks like this. Two charges next to each other can also have potential energy in joules. Use the formula like that. And then similarly, if you want to know how many joules you could get per charge in a given region, before you put a charge there, maybe you're deciding like, hey, should I put a charge there? Is it worth my time? Ask what the V is. That would tell you how much potential energy you get per charge. And that's the electric potential, the V. And this is created by all charges. So one way to think about this is charges create fields and potential around them. And then if another charge wanders by, there will be a force and a potential energy between those two charges. So that's how F and V and E and U are all related. It's good to keep it in mind. You can imagine a map. So they might give you a map of equipotential values. So they like doing this. They're like, hey, these are lines of equal potential. How did they get set up? Who knows? But let's say this is a V value of 10 joule per coulomb. And this V on this line is 5 joule per coulomb, and the V on this line is 0 joule per coulomb. If it's an equal potential line, it means that the V is the same throughout the entire line. So 10, 10, 10, 10, 10, 5, 5, 5, 5, 5, 0, 0, 0. What can we say? Well, if there's no charge in here, nothing. We can be like, well, that's great. There's a field there. No one's there to notice it. Once you put a positive charge in here, stick a positive charge in here, now it's going to interact. What is it going to do? Well, one way to talk about it is it's going to try to reduce its potential energy. How would it do that? If you're positive charge and you want to reduce your potential energy, you're positive here. You want to go toward lower V. It's going to be like, I'm going to fly toward the lower V over here. It's going to fly this way to reduce its potential energy. If you were a negative charge, you would fly toward higher V. Like, why would you do that? Well, because if you're a negative Q and you get multiplied by a higher number, you're going to have a more negative U, right? You're going more into debt. So that also decreases potential energy. Everything's trying to reduce potential energy. Positives do it by going toward lower V. Negatives do it by going toward higher V, but they're always decreasing potential energy. So the force would go this way. What about the electric field? The electric field in a region of equipotential lines points toward lower V. So I got to put my arrows toward lower V. Turns out it's always perpendicular, so you got to cross it like a right angle. I'm not doing the best job here, but it should cross it like a right angle. That's what these electric field lines would look like. In places where they're more packed in, you'd get more electric field, so be careful drawing it like that. So you'd have electric field in here, and then you get another explanation. Look, the electric field points down-ish. Positives feel a force in the direction of electric field, so the force is down-ish. Negatives feel a force opposite the direction of electric field, that's why it goes up. So many different ways to use words to explain how this stuff works.